Good evening, everyone. This is your weekly dose of business analytics. How have you been in the past week? Or, well, how was the week starting for you?
Hi, Jerry.
Hi. That must be short Ray, right?
So
Yeah.
far, so good. Thanks, Jerry.
Oh, great to learn that. Now I'm curious, which part of the homework 5 is bothering the most?
Can we take a look at number 2, Jerry, and how to set up the regression model and organize the data into the different shifts?
Okay.
For one, I like to check C and D and E, like real quick. Like I don't want you to go like in detail in them, but you can
All right.
help
Sounds
us
good.
to kind of
So we have the latter part of problem 1, and which part of problem 2 did you ask for? There was one student, I believe.
Yeah, Jerry, I think just in setting up the regression model and just a refresher on how to do it when organizing the data into the different time shifts.
Oh, okay. All right, got it. Well, let's first take a look at problem 1 then. Now, I encourage you to pull up your Excel file and also your Word document of the report. And let's see how you have addressed the problem, maybe in a similar way or in a slightly different way. Remember that there could be multiple ways to address the same problem, and some of them, some of them might be all correct. So no worries if your approach slightly deviate from the others or the one you found in the answer sheet. All right, let me, well, let's see.
Did you want me to share my answers on this screen?
Oh, yeah, that'd be great.
It's okay. Okay.
Let me first enable my screen share. All right, now I can do so.
Okay. Let me. Okay. Can you see my screen for problem 1?
Yes, I'm seeing that. How about other students? I believe you can also share, see the screen shared by Shore.
We got it.
So, so C is asking, is an exponential model an appropriate way to model this data? Why or why not?
Mm-hmm.
So I looked at the scatter plot for, maybe it would have been easier if I showed my Excel, because I see this is not loaded here for whatever reason. So I think I looked at this model with both of them. So I have to fix this one.
Okay.
And I think this line moves, depends on if alpha is 0.2 or 0.4. Oh, this one. So I have it here, like it's closer to the points, it's further from the points. So this is a better model.
Oh, what's your audio cutoff?
Sure, you're coming in and out.
Yeah, I have been having Zoom issues all day. I'm sorry.
Okay, I
We'll
saw
work it
that.
out.
I saw that you built a good illustration of the model showing from the smoothing model, right? Versus the observed data. Well, this
Yeah.
chart you built in part D is not showing, but I think
It's
that
not
one
showing.
for
I
part
have
C is okay.
I have to fix it. So there's a polynomial here.
Okay, all right. How about we scroll up to see the one you built, the chart you made for part C.
Show it again. Okay. Actually, polynomial shows when I'm not doing screen share. Or
Oh,
whatever.
really? Okay,
Yeah.
I see.
Because everything was fine before I did a screen share, so I don't know what is going on.
How about we see the one in part C? Yeah. Well,
Okay.
in part C, we still see the data, and I mean the scatter plot at least. The trend line, however, my understanding is that this trend line comes from the model you made using the smoothing technique, right?
Yes.
Oh, okay, correct. So as you can see in this trend line represented by the green curve using the smoothing technique, at the beginning, it looks okay. It somehow finds the middle zone between all the points, right? However, we will notice that for later periods, when the week increases, for example, after week 12, we see that it appears that the points are mostly lying above the trend line. Basically, it says that the smoothing technique is underestimating the weekly observation. That's why it doesn't reflect the changes over week in the mean value. And this is also as expected for a smoothing technique, because smoothing is usually built with stationary theories. Now, I have a small challenging question. What's your understanding about stationary theories? What type of time series would be stationary, and what type will not be stationary? Any comments or answers?
Shifts at work are stationary.
Oh, excuse me. I'm not sure whether I understood that part. What did you say?
Working shifts at work, or like number of customers doing different shifts, that is stationary because it's a random fluctuation.
Oh, okay. So I'm hearing two mixing components in your answer. First, it appears that you correctly interpret that a stationary time series is random fluctuation. And this randomness means that there should not be a change in the mean value. So we should not see a trend, but only white noise. That's usually the term used in time series. A white noise is a random walk over the same mean value. So if a time series is stationary, we will observe that we could simply draw a horizontal line that will stay in the middle of the points. However, this is not the case for problem one. In problem one, we are modeling the weekly visits to a new shopping mall over 16 weeks. And if we understand it substantively, a new mall will take some time to grow its customer base, right? And there will be always new shoppers coming in over future weeks. So we see there's a growth in the average number of visitors per day. That's what makes the time series not stationary, but with a trend in a mean value. That's why a smoothing technique may not work that well for time series like this.
So Jerry, that makes sense for our response. I had a little more simplistic response that the trend was steadily increasing over time.
Would you mind sharing with us how you adjust the response?
Oh yeah. I can share what I wrote here. But I mean, I understand what you said, but I just put basically that, continual increase on average each week. Given the trends and correlation of time and visitors continually increases is visible in the small data set, this technique does not appear to be most accurate. I think I'm saying the same thing, but not using the buzzword. So do I?
I see. What's most important is to understand what type of time series smoothing models are built for, and what type it's not built for, and use the correct one to do it. Yeah, you're not required to use some jargon to refer to this type of time series, but it's important for you to understand why a smoothing model may not work as well that well as a polynomial model.
No, I like the jargon. It sounds like I'm somewhat right, but not exactly right, because I'm missing the concept of the time series versus the point in time.
Yeah. However, if you learn more about time series, you will also find that there are ways to adjust stationary models so that it also works for time series with trend, but that involves detrending. So we first remove the trend, then use the rest to apply the smoothing models for. But that's beyond our initial learning about time series. All right, thank you, Shori. Should we move on to part D?
Sure. I just wanted to ask a quick question. When I do graph the polynomial, it does follow the variables much better.
Okay.
Yeah, just I couldn't
was that
show
a question?
that.
No problem.
Because D is asking for that, and
yes,
then he's asking
you're
to
right.
draw
We should
interpretation.
What was your question, though?
Yeah, no, and then you use the regression model to make prediction for week 17. Because you have the intercepts, you have the slopes, so it's just like what we did in previous homeworks, correct?
Yeah. Well, let's take a look together to make sure that we're on the same page. In part D, we are still modeling weekly visits using the index of weeks. So now we fit, instead of a smoothing model, we use a second order polynomial regression model, just as what we did last week in homework 4. It also gives us a form, right? That's very helpful in the homework question. The dependent variable are the weekly visits. Okay, how well does this model fit the data, and what prediction would you make for the number of visitors in week 17 using the models? I see that it's asking the same type of question as last week. So I do not see any new concepts involved in this week's, except that it's applied to time series. Did any of you find part D in problem 1 challenging?
Hi, this is Lindsay, and I just would like to say I find all of this very challenging. So yes, but I do not want to show my screen and do a whole show Ray situation. I'm not that brave. Get it, girl. Good job, show Ray.
Okay. So how will you find to be most helpful if we are resolving problems in problem 1?
The question is, how would it be most helpful? I find all of this very helpful when you go over our homework, Jerry.
Okay.
I like when you start at the top and then you go down to the bottom is helpful.
All right. Okay. So should I illustrate part D, or is there a demand for me to start from part A even?
Jerry, I have a question.
Okay.
So I kind of split this as in exponential smoothing problem 1 and then time series problem 2, but you're saying that we kind of have to see problem 1 in both ways, correct? I'm still kind of confused how time series relates to problem 1. I got the answers right, but I couldn't relate it to time series like you mentioned in 1C. Do you mind I'm sorry for everyone who got it, but do you mind explaining that one more time, please?
Okay. I'm not sure whether I understood your question.
Oh.
You mentioned that you did not understand why the time series is even involved in problem 1.
Yeah. Yes. I mean, or is exponential smoothing
Okay.
like, is that considered a model of time series?
Yes.
Okay. Okay. Sorry. I had a disconnect there. Do you, sorry, Jerry.
Smoothing models are actually mostly intended for time series.
Okay. So for C, to go back to that one, smoothing model would not work because it's not the proper model in a time series data set.
Oh, I see.
Sorry,
Okay.
I'm still a little confused on that.
Smoothing models are designed for time series. That's true. So it works for time series, but only a subgroup of time series. There are many types of time series, and here the difference comes from whether there's a trend in time series. A trend is a systematic change in the mean value. So for a, let me see whether I have the plot. Okay, well, how about I share my screen? Where's the button? Okay, now I'm sharing my screen. You see a scatter plot with a polynomial model trend line. Anyway, if this trend line is not a curve, but a horizontal line, so that there's no change in mean value over time, then smoothing models would work. Because the smoothing model is built for stationary time series. It's not intended for non-stationary time series. So capture the key term stationary here.
Oh, okay. So
Gotcha.
you want to use exponential smoothing when you have a straight horizontal line because there's no change, correct?
Mm-hmm. Yes.
Oh, but because there's an exponential growth in the data set, exponential smoothing would not work. So then you would want to use the second order polynomial, correct?
Correct.
Okay, I got it. Thank you.
Oh, wonderful. It seems we captured an important property and applicable situation for smoothing models.
Jerry, just to conclude, so it doesn't work, the smoothing technique, because it is random fluctuations and it's not a trend. Because
no, you are stating exactly the opposite.
Yes, because it is a trend.
Because it has a trend, so
Uh-huh.
it's not a stationary
Exactly.
time series.
Right,
Therefore, we should not use stationary models. So smoothing models will not work as well as polynomial.
Super.
All right.
So Harry, if I may say, so suppose if we have say shifts from
Well, excuse me, I could not hear you clearly at all. So I'm not capturing any part of your question. Could you maybe use a microphone or type?
Never mind, in the go on, I thought that.
Oh, excuse me, I could not hear clearly, so I'm not. I could not understand your question. All right. while you're fixing your audio, let's see whether other students have questions about part one. Problem one.
While this is up, Jerry, the you're touching on D,
Yes.
and I also got the R square of 97%, or 97%. That seems to me like the best response. That's why you'd want to use this model, because that's a pretty good R squared, right?
I would have to warn you about that, because it's very easy to see a very high R square in any type of time series model. So it's not surprising to see that this R square is 97% or 0.97. So choosing or staying with a model just because of R square is very dangerous decision for a
I couldn't agree more. But so what would be a good? So the question is, I'm kidding, of course, because I use that as my example. So how does this model fit the data? And what prediction would you make for the number of visitors? I said it fit the data well because it's 97% R square. Is that?
Yes, you can say that it fits the data well. That's true. However, there are many more properties that we should care about in a model. And in this case, if our task is to compare which model between smoothing model or polynomial, second order polynomial model to choose, we could use R square. That's not a problem. So we can compare the model for this weekly visitor model between the R square shown here and the one that's reflected by the smoothing technique. But because the smoothing model is not built from linear regression, right? We could not directly get this R square, but it's possible that we still derive this R square in a different way.
Great, thank you.
All right. So I'm curious how you addressed part E. Would one of you want to share your how you answered part
exponential model we cannot predict week 18 through exponential model, right? We can only use the polynomial to fit in the week 18.
Yeah, correct. You're correct on that point. Smoothing technique will not allow us to extrapolate. Well, I guess it's not really interpolate. Only the second order polynomial model will allow us to expand the
beyond one more time period, right?
Yeah. And how did you estimate the number of visitors for week 17?
Using which model? If it's exponential model, if you type in week 17 on cell A18, that will be your estimate.
So you could use the Y formula on the graph, but I think he said that he prefers if you use the formula off of the regression model and use the intercept and the slopes there.
Yeah. Great question. Great answer as well. Because we built two models for week 17, it's okay that smoothing model still works for one step ahead. But if we want to, expand it even wider, so if we want to predict week 18, then this exponential smoothing will not work for a future week beyond the 17, because if we move the same formula to one step ahead, you see that there's an error here. It's trying to predict week 18 using week 17 observation, because there was no observation for week 17, but only a predicted value. So this Excel automatically treats this empty cell as 0. That's why you see there's a huge difference between week 17 and week 18 prediction using a exponential smoothing. That's because the week 18 prediction was built wrong. It should not be there. But we could still predict using an exponential model like shown here. We can, well, let's see. Well, I do not have the generated output of a regression model, but using the coefficients in the summary output, as mentioned by Shori, we can use this formula of a second order polynomial model to predict what happens in week 18. All right, seems we solved problem 1. Any questions? All right, shall we move on to problem 2? Which part did you find problem 2 to be most challenging?
Yeah, hey Jerry, it's Lindsay again. I just wanted
Hi,
to go
Lindsay.
ahead and suggest starting at the top of number 2 and then
Okay,
working our way right on through it.
so how about we start from part A?
Thank you.
All right, so here we see a slightly different model that's involving that involves seasonal variation. We call it seasonality, but this season may not be just 4 seasons in a year. It could be day of week, it could be week of month, it could be day of month, it could be morning, afternoon in a day. So do not confine the definition of seasonality to be 4 seasons in a year. And then in this case, in problem 2, we see that seasonality comes from let's see, well, both a day of week and let's see, not day of week. I'm seeing that it's time of day. The reason is we need more than well, 2 cycles or more to find a seasonality. So for example, if we have only 1 year of data of 4 seasons, we could not model seasonality of the 4 quarters at all, because we need a few more observations to estimate the parameters or the coefficients in a model. With just 4 observations, we could not really build a model with 3 different seasons. We will see instead a perfect prediction, but the model won't be useful. Instead, if we want to model seasonality using 4 quarters of a year, we should have at least 2 years of data. So we see that there are 2 cycles of 4 quarters in a year. In this case, we do see that there's a day of week from Monday to Friday and from Monday to Friday. So we could possibly build a day of week seasonality. However, we also see a shift between time of day. Let's see, there are 5 shifts. So we could use 4 indicators of the shift of the day. Remember what we did last week. In last week, we saw a model to predict house prices in Orange County. One of the predictor is the city where the house sits, right? So out of the 4 different or unique cities, we used 3 dummy variables to represent the city of a house. In this case, because we have 5 shifts, so here I am using 4 indicators to represent shifts. Any questions here? So are you all good with building indicators for out of a categorical variable?
Jerry, I didn't have a problem doing that. I got the 4 shifts, but then how you named the periods and you went down that way. One of the things I remember Thomas sharing was how, like, because there's 5 times in the day, right? So he did like named those periods, like we put it 1 through 5, and then he just kept repeating that. So that's what I did, but clearly that's wrong because you named the periods all the way down. That's where I got a little confused.
Okay, I'm not sure. I couldn't understand how your approach is different from what I'm showing here.
I got all the shifts I got all of those, but how to the left of shifts you have period.
Okay.
That was the part I got a little confused on because you label them 1 through whatever. But one of the things that Thomas was showing in class was see how they're repeating series like 8 to 10, you know, there's 5 repeating series every day. So instead of doing the periods 1 through whatever, I repeated them like 1 through 5 every time for every day.
Oh, I see. That'll be wrong.
Yeah, I got that because my graph looks very funky. So yes.
Yeah. This period is here because we want to show a growth in trend. So what's your name, by the way?
My name is Des.
Oh, Des. Okay. What Des did instead, she was doing like this. She was repeating these periods from 1 to 5. Then she did again for week for the next day. So in Monday, she was representing the periods using 1 to 5, and on Tuesday she did that again. This approach won't reflect a growth through each day because it sets back the period again for a new day. Then it doesn't reflect how what's growing here. It's a branch of office, right? And number of customers, right? If the period is represented in the top 10 rows here, then it doesn't reflect that there's a smooth growth in the number of customers on Tuesday than Monday. So we must reflect this part.
Thank you for explaining that, because my graph looked to your point where it just kept repeating. So thank you for clarifying that. I appreciate it, Jerry.
Yeah. My pleasure. So using this type of period, we are saying that removing, because we are setting everything as constant, right? And here the constant in shifts is very apparent. We could refer to either the missing category. Here it's shift 5 because we are comparing all the shifts to shift 5. So when every indicator from shift 1 indicator to shift 4 indicator all take the value of 0, it actually refers to shift 5, right? See that it's apparent here for shift 5. That's this. That's 4 p.m. to 6 p.m. on Monday. That's actually the last shift on each of business day. All these indicators are 0. So that's why I'm saying when all these 4 indicators take the value of 0, it's actually referring to shift 5. That similarly appears missing in these indicators. However, its information is still captured. So to interpret this period, we could say that when the shift moves, when time increases by each 2 hours, the number of customers is expected to grow by 0.22. That's what this period represents in this model. Any questions here? Well, now I have a question for you. How do you interpret the value of shift of coefficient for shift 2? This coefficient is estimated to be -20. Any volunteers? How would you interpret the coefficient of
Yeah, so that's going to be
shift 2?
you're going to take the most away from the total, so it's going to be the fewer calls on the shift.
Oh, excuse me. Could you state your interpretation of this coefficient again?
Yeah, I didn't word that well at all. So shift 2 is the largest negative, so that would imply that it's probably going to have the fewest calls per shift.
Oh, right. Yes, you're right on that part. However, in interpretation, it's best to combine both qualitative and quantitative information so that the interpretation is as specific as possible. If I were to do it, I would say that there's a significant oh, by the way, I have a question actually for you. Whether we have learned about p-values.
We haven't.
Oh, I haven't. Okay. Have we learned anything about t-tests?
No, just mention in our
Oh, I
economic,
see.
like with
Okay.
this sentence.
Now
No
I
allowed.
got it. We will learn about these concepts in a future week. However, let's just stick with coefficients alone then. So to interpret this coefficient, I would say that controlling for a smooth growth, the second shift in a day compared to the last shift in a week, in a business day, we will on average have 20 fewer customers. So you see that here, first, I did a procedure stating that this coefficient is the effect after controlling for other factors. The other factors in our model is this period, because it won't make sense if I control the value of shift 2 without any change in shift 1 or shift 3 or 4 indicators. Because if I'm talking about any information regarding shift 2, this shift 2, if I'm making predictions about shift 2, this shift 2 dummy variable will take value of 1. At the same time, the other shift indicators, shift 1, 3, 4, will all take value 0. So I cannot change the value of one shift without changing the value assigned to the other shift indicators. So although usually we apply the term saying holding everything else constant, right, when we describe effects in a multiple linear regression, we also need to remind ourselves what it means. In this model, it won't make sense if we control for the value, if we assign a new value to shift 2 without changing the value to the other shift indicators. However, this period is not captured by any shift dummy variables. So it does make sense to control for period when we change the value in shifts, or vice versa. We could control for the value assigned to shift indicators, but change the value in period. And this is the first part I did, controlling for some variable while changing other variables. And the second part is that I put the interpretation within the context. I also referred to this coefficient explicitly by saying that this coefficient represents the difference in the expected number or the average number of customers visiting the bank, right? The difference between second shift, that's 8 to, that's 10 to 12, from the last shift, that's 6 to, well, that's 4 p.m. to 6 p.m. Any questions regarding interpretation?
Can you repeat the very last part when you were comparing two shifts?
Oh, okay. Yes. I'm comparing two shifts because the specific way I built these indicators. Here, I'm choosing shift 5 to be the reference. So that's why you're not seeing the variable shift 5 here, because it's used as the reference group. Everything is to be compared with shift 5. Remember what we learned from past weeks, that the intercept represents the predicted value when every predictor takes the value 0. So this is exactly reflected here, because all these shift indicators 1 to 4 will all take value 0. See, for this one, the last shift on Monday, and also Tuesday, and also Wednesday, and so on. You notice that all these shift indicators take value 0. So that's why when describing the coefficient of any of these indicators representing shift, we are actually comparing shift of corresponding to this one value for a dummy variable to the reference group. The reference group in our case would be, in my case, would be shift 5. However, you could possibly build a different version of the model with the same quality of prediction as what we practiced last time. For example, I could still build a shift 5 indicator, and I remove this variable, hide. So you could use shift 1 as the reference group, but use shift 2 to 5 to build the indicators. And as we saw last time, this would give us a model with the same R², but the coefficient names, because they are representing different shift of the day, right? We will have different values. The way to interpret, no matter how you build the shift indicators, is always the same. To talk about the difference between the reference group and this one. So for example, this reference group in my fitted model is shift 5, right? And because of the way it's built, see that shift 5 will take value 0. So its coefficient could be also understood as 0. So here, if I describe, let's change for another one, shift 4. I'm saying that this number 14.7 negative is the difference between shift 4 and shift 5, holding the period to be constant. When the period is constant, it could actually mean that we are talking about the same day, right? So it means that if the day of week is held constant, shift 4 would be on average having 14.7 fewer customers than shift 5, the last shift of the day.
That was very helpful. Thank you, Jerry.
No problem. Did I make it clearer?
Yes.
Okay, glad to know that. However, you also, let's see about part B and C. In part B, we are asked to ignore any possible trend effects. And it asks which of the 5 shifts attracts the most customers. Which shift has the least customers? Carefully explain your answers. Okay, I believe I just provided at least a hint for the second part of the question, which shift has the least customers. Now, I would like some of your answers about how you addressed the first part in the question. Which of the 5 shifts attracts the most customers?
Can I try this one?
Yeah, sure. You're very more than
I'm
welcome.
thinking shift 5 gets the most customers and shift 2 gets the least customers.
Okay, how did you pick the most popular shift?
Because from my regression, I see, so I had it done the same way as you did, 1, 2, 3, 4, and 5th was all zeros. And all of these other are negative coefficients. So that means shift 5 gets more than all of these. Which is why I'm saying shift 5 gets most. And then shift 2 has the most difference from that higher number. So that gets the least compared to that number. The others are also less than shift 5, but 2 is farthest out.
Oh, great. That's a great interpretation. So who was it?
Daniel.
Daniel, oh, okay, wonderful. So he has a brilliant answer here by picking shift 5 to be the most popular shift, because compared to shift 5, all the other 4 shifts have a negative coefficient estimate. Those suggest that shift 1 to 4 were estimated to have fewer customers than shift 5. That's what makes shift 5 to have the most customers. All right. Any questions about part B? Okay. In a future week, we will also learn what represents by p-value. So here, what I noticed is that this p-value is larger than 5%, 0.05. So it suggests that although shift 1 has a negative estimate of the coefficient, this could have happened because of sampling errors. It means if that we observed the bank many times or many weeks, this coefficient, then we acquired more data. Then when we re-estimate the model, we could see that this coefficient is not significantly different from 0. That also represents that shift 1 and 5 would have comparable number of customers. So do not take a negative estimate or a positive estimate to be surprising. Or that also means when we interpret a coefficient, we should also pay attention to not just the sign, but also the magnitude and also the statistical significance. We will learn more about statistical significance in the future.
So Jerry, quick, in reality, is it shift 5 has the most and shift 3 would be the least, since p-value is less than 0.05?
Yeah, if we hold that to be the threshold, yes, I would announce that the shift 3 coefficient representing the difference between shift 3 and shift 5 number of customers is significant. It means this difference that's almost about -4 is significantly different than 0. So it's very unlikely that we have this coefficient estimated simply because of sampling errors. That also means if we survey this bank again and again for many weeks, we are also very likely to see a negative coefficient estimated for shift 3 compared to shift 5. However, this cannot be stated for shift 1 because this coefficient is too close to 0, so that we are not so confident that it's significantly different from 0. All right, let's move on to the last part. Now you will be able to address all parts of our week 5 questions. Based on the model, what prediction would you make in terms of how many customers comes to the bank between 10 to 12 on Wednesday of week 3? I would predict, if it's challenging, then it's mostly about how we assign values to observed predictors. Has any of you already done part C? And how did you address this question?
So Jerry, I continue the periods down for the next 3 days, and I think that second shift is period 62. So I use that, and then I put it back into the equation for shift 2.
Ah, sounds brilliant. So who was it?
Stephen.
Oh, Stephen. Excellent. So what Stephen did was that he extended these values until he found the one corresponding to Wednesday of a future week. Let me practice what this will look like. So first, I would like to freeze the first pane so that I see, well, top row. So I see the variable name all the time. So let's see what happens in week 3. So these things would be all repeated, right? So I'm just going to copy and paste everything. Oh, well. Let's see, number of customers. This is number of customers is the dependent variable. So we cannot really drag and autofill the dependent variable, but we could do this for the time periods because this is how the period will be represented in a future week, right? There's no uncertainty in a time period indicator. We would do the same thing for, let me hide this part. Remember, I built the model using shift 5 as the reference group. So this would be shift 1. So for Monday, it will also look like this. Tuesday and Wednesday. Now we have all the independent variable indicators represented. Any questions here? All right. Using this information and the coefficient estimated in this model, I could possibly predict what happens on Wednesday. Let's see. This question asks for Wednesday on shift 2. So it'll be this one. And Stephen also found that the period will be 62. The indicator for shift 2 would take a value of 1, whereas shift 1, 3, and 4 will take a value 0 because all of these are to be compared with shift 5. Any questions here? Now I can make a prediction. It follows the same idea as many times as what we practiced before. It starts from adding the intercept, then the multiplication between period coefficient and period. This period would be this. Well, this value, which is 62. We do the same thing for all the other coefficient and indicators times it'll be this value, although I know it's 0. And we also take the multiplication between coefficient of shift 2 and the indicator dummy variable value of shift 2, which is 1 in this case. And next part. Interesting. Okay. It seems I forgot to. Time is okay. Now it's correct. Let's move on to shift 3. Shift 3 coefficient times shift 3 value of the dummy variable. Now it comes to the last part, that's shift 4 coefficient times shift 4 indicator value, which is also 0 in this case. And using an enter, I see this is the estimated value using the model with the period and shifts. So as a any questions in problem 2?
So Jerry, one question that I have, do we not need to build out dummy variables for the day of the week then? We just do it for the shifts?
Good question. Let's we could build a model with day of week. It's not required in any part of the homework question, correct? I've not seen that.
I guess I don't think so.
But we could do so. Let's see what happens. I'm also slightly curious. So first, let's change the reference category for shift. I'd like to see what happens if I use this, well, first shift of the day. If this one equals, let's see. Last one would be 4 p.m. to 6 p.m. Then it takes value of 1, otherwise value of 0. I hope it works. Okay, it's working as intended. Now let's build a few indicators for day of week. So saying Monday, Tuesday, Wednesday, Thursday. I'm leaving Friday out of this because I want to use Friday as the reference group. That means to assign the values for these indicators, we will let Excel understand that if the day of week is Monday, then it'll be 1, otherwise 0. I would use the similar formula for the other few indicators, but change the checking point so that this is instead of Monday, if the day of week is Tuesday, this would take value 0. If it's day of Wednesday, then the indicator for Wednesday would take value 1. If the day of the week is instead Thursday, then this indicator for Thursday would be 1. However, because the first day is Monday, right? So that's why we see that only Monday takes the value 1, while all the other day of week indicators take value 0. Now let's see what happens if I autofill the indicators. You notice that for all shifts on Monday, the Monday indicator all take value 1, whereas all the other 3 indicators representing business day take value 0. This happens to Tuesday observations. Only Tuesday, the variable, the dummy variable for Tuesday takes value 1. This happens periodically for other day of week. So remember that only the observation until week 2 would be observed. So we could build a model. Let me think. I see. Possibly I will have to move the period so it's on the same in the same range of the observed of the predictors. But let's see whether Excel allows me to do that. Regression. Oop. First, we select Y. Remember that we only have 2 weeks of observation. Second, we select X range. I don't believe it allows me to select range that are not continuous. So if I have a period plus 4 shifts, I'm not sure how I can join another range. Maybe I can do this. I have label. Okay. There's a formula. If I change it to comma, will that make a... yes, it must be continuous reference. That's why I probably will have to move this period. One of the reasons I don't use Excel for my data analysis. Okay, anyway. Regression. Now here I can use column G to column O. And it also appears that Excel, when doing regression, doesn't allow any missing cells. But other okay, let me just try it again. All right. I'm going to put my model here. All right, this should all work this time. All right, this time I have a few more predictors representing day of week. Okay, well, it appears maybe they're not necessary since the day of week estimates are also very close to 0 and the p-values are large. In a future week, we will learn that when this happens, it means that the predictors added may not have added substantially a lot more predicting values. So ignoring these additional variables may actually simplify our model without harming the predicting power. We always want to use a model that's as simple as possible without losing too much details or predicting power. So if we compare this with the model we just had, well, maybe I can copy and paste to the one I have here. So on the left, we have a model that's as prescribed in problem 2. We use a period plus 4 shifts to represent the time series. On the right, I added a few more indicators for day of the week. We noticed that the R² is not improved substantially. On the contrary, if we use adjusted R², we actually see that with 4 more predictors added, the adjusted R² was actually lowered. This is possible because our adjusted R², if you read my notes in the review session for the additional resources about our adjusted R², adjusted R² also adjusts for overfitting. It's if we added more predictors, I'm sure you have learned this part from Professor Apple. When adding more predictors, it never lowers R². So R² is also always increasing when we add even not so useful predictors. But to penalize this, we some statisticians came up with the idea of adjusted R² so that we penalize for too many predictors added to the model. So we see that this more complex model has a lower adjusted R², meaning that the added predictors are not contributing to the model predicting power substantially. So we don't really need day of the week.
Perfect. Thank you for explaining that, Jerry.
All right. Yeah. Another comparison you can notice is that the coefficients built for the shifts will be different because I'm using, instead of week 1 to 4 indicators, I'm using week 2 to 5 indicators. However, you will find that the comparative relationship will not be substantially changed for those significant predictors. For example, on the left, we're comparing all the shifts with shift 5, right? So that we find shift 2 and the shift 4 have the fewest number of visitors. This is the same in the to the right. When using shift 1 as the reference group, we still see that shift 2 and shift 4 have many fewer customers. This substantive conclusion won't change because we chose a different reference group. All right. Any questions regarding time series models?
Hey, Jerry, any chance you could click on the cell from the formula that you put in on the bank tab to answer that last question?
To answer the last question, it was about the prediction, right? So which are you asking about how this was estimated?
Yeah, the third, yeah, exactly.
We simply need to substitute these assigned values to shift and period for the regression equation. So here, this formula is nothing but the regression equation reflected by this fitted model. It's the same technique as what we used last week and the week before the last, and maybe also the week before the last. So we always use the regression equation to make prediction. Excellent.
Great, yeah,
Well,
appreciate it. Thank you.
Before we conclude our day of discussion, I have a small challenging question for you. I'd like to your comments about whether the model we built here in part C, right? Or part A of problem 2. Do you think this relationship reflected in this model is causal? Yes or no?
Could you repeat the question?
Yeah. Do you think the model we developed in part A of the problem 2 reflects causal relationship?
I'd say no.
Okay. Who was it?
That was Edham. Wait a second. That was the mall question, or which question?
The bank question.
Oh, the bank.
Mhm. So Adam doesn't think the bank question model reflects causal relationship. Do you all agree? Or do you have different comments? Now, corresponding to that, how about the mall attendance question? Do you think the second order polynomial model reflects a causal relationship?
Yes.
Yeah, I'm trying to.
Okay.
Yeah,
So
there's a
you're...
Sorry,
Okay.
Jerry. Go ahead.
I was trying to follow up with Adam's comments. He didn't think the relationship reflected in problem 2, the bank visitor problem, to be causal, but he considered the one for this weekly attendance problem to be causal. Why did you have this contrasting conclusion between these two models?
Because the mall seems to me as if it's a trend,
Okay.
that's a causal, but the other one is random. We called it fluctuations. Random. Then since
Okay.
it's random, then it's not causal.
Ah,
thought about
okay.
I'm not sure.
That was your reason. Okay. How about other students? Did you have a similar or different interpretations about whether these two models are causal or not?
When I did the, hi, it's Mark. When I did the line graph for for problem 2, it was all over the place. Whereas the graph on problem 1 is very accurate and the line follows it perfectly.
Okay, so did you consider which of these two models to reflect causal relationship?
Problem 1 was causal all the way, but problem 2, the line graph was very irregular, so not causal.
Okay, I see. Interesting thinking. How about other students? Do you have different thoughts? And the last comment was made by owner. Oh, okay. I like your alias.
Mark. It's Mark.
Oh, okay. Is owner actually part of your name? That sounds very cool. Okay. If I were asked for this question, I would say that neither of these two models reflects causal relationship. First, it could be a misunderstanding among even on some online blogs you could find. Some said that regression models reflect causal relationship, whereas correlation coefficient does not. This is absolutely wrong, because causal relationship, when the data generating process is designed in a specific way, could also reflect causal relationship. On the other hand, if the data generating process is not designed to detect any causal relationship, then even if you use the most advanced regression model, you still will not find a causal relationship. So what reveals or what reflects causal relationship is not depending on whether we use a model or whether we use correlation coefficient. It totally depends on how we designed the data. How we design the data also affect how the data was generated. So that's why I used the term data generating process. In our both cases, the first one was weekly visits to a new shopping mall. We are waiting for the data to generate itself. We are not manipulating anything. So the relationship between time and the number of visitors is nothing but observational. So although this has a curve that someone considers to be a very accurate prediction, it doesn't reflect a causal relationship. On the other hand, for problem 2, when we build this model with let's see, number of customers on different shift of a day to a bank, it's not causal relationship because we are not manipulating any experimental variable at all. We are just observing what happens through 2 weeks. So this model built with this R squared is almost 90%. Is also good prediction according to some of your threshold. It's good prediction, but it's still not reflecting causal relationship. Both of these models for problem 1 and problem 2 are reflecting only observational relationship or association. But don't get disappointed. Association is also very useful. Not all models were intended to seek any causal relationship. For example, if you as a manager of the shop or a manager of a bank, you don't really want to, you don't necessarily need to check a specific program or promotion to see whether it boosts your customer visits. On the other hand, your purpose is simply to understand the weekly or daily variation in the number of customers so that you can efficiently assign let's see, what you call that, the schedule of work, right? Then this is enough. We are not always seeking causal relationship. On the other hand, if you are tasked to check whether, for example, a specific local internet promotion makes your customer base to boost. In this case, you do want to use some causal relationship technique to find the causal relationship here. So if your attendance to the mall is growing over time, this is as expected. Without any promotion program, you will still see this growth because you have a new mall, right? New customers will come in just because they want to see a new mall, what's inside. But if you want to see the additional effect of doing promotion to justify your budget on internet advertisement, then you do want to see what the net effect is. This is where causal relationship would be helpful. However, none of our models were built in this way, so they are not telling a causal story at all. All right. Did you find our last part discussion useful? Or I hope it, yeah, because I'm introducing some new concept that may not necessarily discussed in the lecture. So if you can see, you find that to be too much additional questions to consider, then feel free to not have it on your burden. But I hope what we discussed this week is good enough for you to address the questions in homework 5. And enjoy a wonderful week.
Jerry, quick question.
Oh, all right.
So if it's not causal, then why we're trying to predict things?
Okay.
You know, since it's
good
like,
question.
I would call this model as descriptive rather than predictive.
Yes.
And with that being said, since it's not causal, then It's not reliable to make predictions on how many I will.
No.
No.
Causal relationship has nothing to do with reliability. And as you mentioned, the model are observational.